This video presents an introduction to drilling and sampling procedures in geotechnical practice. A thorough knowledge of the tools and procedures is necessary for planning and executing an effective subsurface investigation. The extent and type of exploration depends on the specific project. For example, the design of a county road may only require explorations to a depth of 20 feet, while the design of the foundation for a high-rise may require knowledge of soil characteristics to a depth of a few hundred feet. At remote sites, all the necessary information may have to come from new soil explorations. In highly developed areas, the extent of soil exploration may be reduced based on information from the surrounding sites. The type of investigation is also greatly affected by the soil type and variability. A structure founded on a homogeneous layer of clay may require high-quality samples to accurately predict the amount and rate of settlement. But if the same structure is on soil consisting of pockets and lenses of clay, silt, and sand, information of greater value may be obtained by taking a greater number of less expensive disturbed samples to determine the location and size of these pockets and lenses. These views of alluvial sand and gravel deposits are shown to emphasize that even relatively homogeneous deposits can have complex interlayering and heterogeneity on a local scale. An appreciation of the inherent complexity of geological deposits is needed for planning or interpreting subsurface explorations. To perform an effective subsurface investigation, the project engineer must be familiar with the tools and procedures, understand the effects that drilling and sampling can have on lab and field tests, and appreciate the inherent uncertainties involved with characterizing subsurface conditions. Most subsurface investigations are performed using drill rigs of numerous types and sizes. Drill rigs can be classified into four basic categories: highway, off-road, over water, and portable drill rigs. Highway drill rigs, the most common, are mounted on the back of an industrial truck, allowing high mobility and minimal setup time. A highway rig is used for sites that are relatively level and easy to access. Off-road drill rigs are used when access to a site is unusually difficult. Typically, these drill rigs are either mounted on large rubber-wheeled trucks or on tracks. If an off-road drill rig cannot directly access a site, a helicopter may be used to move it into position. For soil investigations beneath bodies of water, an overwater drill rig must be used. Some overwater rigs consist of a customized barge, where the drill rig is positioned in the center and drilling takes place through a hole in the deck. Portable rigs can be partially machine-operated, as shown here, or operated manually. These rigs typically have a depth limit of about 25 feet, depending on the subsurface conditions, and are used when access by an off-road rig is impossible and the expense of a helicopter is not justified. In any drilling program, the first step is to check for all possible underground utilities or obstructions, and get an underground service alert clearance as required by law. No drilling should begin without this clearance, no matter where the site is. After the drilling is completed, all boreholes or piezometer installations must be sealed in accordance with state and local regulations. Here a highway drill rig will be used to demonstrate the general features and procedures that are common to all drill rigs. After the drill rig is positioned over a borehole location, the mast is raised and secured and the drill rig is leveled. If the rig is not level, the borehole will be angled, causing great problems in drilling and sampling, in addition to producing an inaccurate soil profile. The drill head, located near the bottom of the mast, is raised and lowered using hydraulic controls. The drill head is connected to a gearbox which enables the driller to adjust the rotation speed to suit the current drilling conditions. A number of cables controlled by winches run to the top of the mast and back down to the hole. These are used for removing or attaching drill rods, auger flights, or sampling tools. Many methods of drilling have been developed, but only four prominent drilling methods will be discussed here. These four methods are solid stem continuous flight auger, hollow stem continuous flight auger, mud rotary, and coring. The main purpose of all drilling methods is to obtain representative samples of the subsurface strata at different depths. These different drilling methods are individually suited to different soil and rock conditions, and thus more than one method may be needed on a given project. The solid stem continuous flight auger method is the simplest drilling system with only two basic components, the drill bit and the auger flights. The drill bit is located at the tip of the drilling stem, with the stem consisting of individual auger flights connected together. When rotating, the drill bit cuts and loosens the soil, enabling the flights to lift the soil out of the hole. Variations of the two most common types of bits, the finger and fishtail, are pictured here. Flights of auger are typically 5 feet long and come in outside diameters ranging from 4 inches to 14 inches. The connections between the drill bit, auger flights, and drill head use male and female connections that are secured by auger pins. The borehole is advanced by hydraulically lowering the rotating drill head as the auger and bit penetrate the soil. Flights of auger are added to the system as needed. Upon reaching a specified sampling depth, the borehole is cleared of cuttings. The augers and bit are removed by a cable. A sampling tool is then lowered down the open hole to take a sample from below the hole bottom. After sampling is completed, the bit and flights of auger are lowered back down the hole, reconnected to the drill head, and drilling is resumed. This drilling approach only works for soils where the open borehole does not collapse. Hollow stem continuous flight auger drilling is similar to the solid stem method in that the hole is advanced and soil is removed by the flights on the augers. The primary difference, as seen on the right, is that the auger flights are hollow. This allows a sample to be taken by lowering a sampler down through the hollow stem, thus eliminating the need to remove the auger from the borehole. The basic hollow stem setup is shown here. The inner bit is connected to drill rods that run through the hollow stem, and the other bit is bolted to the bottom of the lead auger. While drilling, the inner and outer bits rotate together, cutting and loosening the soil at the bottom of the hole. The soil cuttings are carried upwards by the auger flights to the top of the hole. To sample, the drill rod to cap adapter is removed, and the drill rods in the center bit are withdrawn from the hole. A sampler is then connected to the bottom of the drill rods and lowered down the hole for sampling. After sampling, the center bit is reconnected to the drill rods, lowered back down the hole, and drilling is resumed. Hollow stem augers use two types of connections. The auger on the right uses a 2-key connection, while the auger on the left uses an octagonal connection. Hollow stem continuous flight augers typically come in 5-foot sections, with inner diameters from 2 1/4 inches to 12 1/4 inches. The outer bit has replaceable teeth, in which rollers and cutters can be inserted to adapt the bit to different ground conditions. The common inner bits are the fishtail and stepwise bits. The main advantage of hollow stem augering over solid stem augering is that the drill rods and center bit may be removed at any time to allow for disturbed, undisturbed, or core sampling. Also, the borehole is supported by the flights of auger, eliminating any possibility of the hole collapsing. This makes it possible to drill with a hollow stem auger in sands below the water table. Mud rotary, or rotary wash drilling, is very different from the continuous flight auger methods. The underlying principle is that mud, a mixture of water and bentonite, circulates through the borehole, bringing the soil cuttings to the surface and supporting the sides of the borehole. For drilling, a bit is connected to a series of drill rods that are attached to the drill head. Drill rods typically have an outside diameter of 1 5/16 inches to 3 1/2 inches and are attached together using connectors like the ones shown here. Common rotary bits include drag bits, roller bits, and plug bits. The replaceable drag bit, one of the most common, consists of a barrel, bowl, blades, and connectors. This design is economical since worn teeth can be replaced rather than replacing the entire bit. The cone bit has teeth on the surfaces of cones, which rotate as the bit is turned. The spacing and size of the teeth on the cone depend on the type of material to be drilled. Plug bits come in 3 basic types: concave, pilot, and tapered. The concave plug bit, pictured here, is designed for drilling through relatively soft rock. An important difference in bits is whether they are face discharge or side discharge. Face discharge bits discharge the drilling mud straight out the end of the bit onto the bottom of the hole. This jetting action can disturb or erode the soil at the bottom of the hole. Side discharge bits discharge the drilling mud out the sides of the bit, and are usually preferred because the soil at the bottom of the borehole is less disturbed. The mud is a mixture of water and bentonite, which creates a slurry with a density slightly higher than that of water. This higher density helps in the removal of cuttings, preventing them from settling on the bottom of the hole. It is important for the slurry to have the correct consistency. If it is too thick, it can clog the pump, and if it is too thin, it can leave cuttings at the bottom of a hole. The drilling mud also supports the borehole walls, and thus uncased holes can remain stable in sands below the water table. If a piezometer is going to be placed in the borehole, biodegradable products may be used instead of bentonite mud. Biodegradable products avoid the permanent sealing effects that bentonite mud has, and thus won't adversely affect the piezometer's performance. There are several components in the mud circulation system. A pump draws in the mud and sends it under pressure through the top of the drill head and down the inside of the drill rods. After it is discharged from the bit, the mud picks up the soil cuttings and carries them upwards in between the drill rod and the sides of the borehole. At the top of the hole, the mud pours out through a catch screen into a mud tank or settling basin. The mud tank has several different compartments that allow the cuttings to settle out. At the other end of the mud tank, the pump again draws the mud, which is now free of cuttings, for reuse. The drilling mud also serves as a coolant for the drill bit, preventing excess wear. It is very useful to check the cuttings as they enter the mud tank and to record any variations in the color or consistency. Such variations in the drilling mud can identify contacts between different soil strata. Operators may also detect changes in soil strata by changes in the drilling effort required to advance the hole. Sudden losses of drilling fluid can indicate that hydraulic fracturing has occurred or that a coarse free draining strata has been encountered. These types of information can supplement discrete samples and improve interpretation of subsurface stratigraphy. When mud rotary drilling in cohesionless or highly erodible soils, an outer casing is used to create a closed circulation system. Casing is advanced concurrently with drilling until it is seated in dense, unerodible soil or rock, creating a closed circulation system. A shoe, made of hardened steel, is attached to the bottom of the lead casing to prevent the casing from buckling while it is driven into the soil by the hammer. Upon reaching a desired depth for sampling, the drill bit and rods are no longer advanced. After the mud has cleared all cuttings from the hole, the drill rods are withdrawn from the borehole and the lead rod and drill bit are disconnected. The sampler is then attached to the drill rods and lowered to the bottom of the hole. After sampling, the lead rod and bit are reconnected to the drill rods to continue drilling. Generally, the mud rotary method is faster than other methods and usually results in less disturbance to the soil being sampled. This method, however, can have difficulties in gravel and cobble layers because the drilling fluid may drain freely into these layers, or the drilling process may not break up the larger particles or remove them from the hole. In the latter case, the drill bit and stem may bind in the hole. Despite these difficulties, mud rotary drilling generally works better in gravelly deposits than either solid stem or hollow stem augers. Coring of rock or very hard soils is similar to mud rotary drilling, with the exception that sampling and drilling take place concurrently. To drill and sample simultaneously, a core barrel replaces the rotary bit at the end of the drill rods. The conventional core barrel is comprised of a core barrel head, an outer barrel, an inner core recovery tube, a reaming shell, a core lifter, and a coring bit. When assembled, the coring bit is attached to the outer barrel, which is connected to the core barrel head. This section is connected to the drill rods and rotates at the same speed as the drill head. The inner barrel is connected to the core barrel head by a ball bearing connection, which allows the inner barrel to remain stationary while the outer barrel rotates. As the core barrel is rotated and lowered, the core bit cuts an annular section out of the soil or rock. This section, called the core, moves up into the inner barrel where it is protected from potential erosion by the circulating fluid. Once the inside of the core barrel is full, drilling is stopped and the core barrel is removed from the hole. By disassembling the core barrel, a continuous sample of the soil or rock is recovered. The sample is measured, identified, and stored in core boxes. After reassembly, the core barrel is lowered to the bottom of the hole and drilling and sampling are continued. Coring drill bits come in three basic types. Pictured from left to right are the diamond, carbide, and sawtooth. Diamond bits are the most versatile since they can produce high-quality cores in materials ranging from hard or very dense soil to hard rock. As shown, coring bits come in a variety of shapes and sizes, each of which is suited for a specific situation. Some systems, such as the Christensen 94 pictured here, can perform multiple tasks such as drilling, coring, and sampling. Wireline retrieval systems expedite coring by removing only the full inner barrel from the hole, thus retrieving the sample while leaving the outer barrel and drill rods down the hole. The type of coring equipment and operating procedures can greatly affect the quality of the retrieved rock cores. Rock cores can be heavily fractured and damaged by the coring process. Failure to distinguish between natural and drilling-induced fractures on the drilling logs can lead to a completely erroneous interpretation of a rock mass's characteristics. Alteration to the drilling equipment and procedures can significantly improve the core quality and percent recovery in many situations, and these changes should be recorded on the drilling logs. We will now discuss methods used to sample soils, thereby allowing the characteristics of soil at discrete points to be evaluated. The choice of sampling method depends on the intended use of the soil samples. Lab measurements of engineering properties such as strength, stiffness, compressibility, or permeability can be strongly affected by sample disturbance. However, time and costs increase rapidly as the degree of sample disturbance is decreased. Therefore, it may be preferable in some situations to obtain relatively inexpensive, lower quality samples during the initial exploratory drilling program. On the basis of the information obtained from such poor quality samples, the need for more elaborate sampling procedures can be judged. The split spoon sampler, also referred to as the split tube or split barrel sampler, is the most commonly used soil sampling device. The split spoon sampler is a thick-walled sampler and provides disturbed samples only. A disturbed sample contains in situ material in proper proportions, but is so disturbed that the lab test to determine engineering properties would not be representative of the in situ conditions. Disturbed samples are generally used for identification tests including visual classification, water content, grain size, and Atterberg limits. The split spoon consists of a barrel shoe, a split barrel or tube, a solid sleeve, and a sampler head. When the sharpened, hardened steel shoe and solid steel sleeve are unscrewed, the two halves of the split spoon may be separated and the sample easily removed. Generally, split spoon samplers are available with inside diameters ranging from 1 3/8 inches to 4 1/2 inches, and in standard lengths of 18 inches to 30 inches. The split spoon sampler, with an outside diameter of 2 inches and an inside diameter of 1 3/8 inches and a length of 24 inches, is the most common in practice. For sampling, the split spoon is attached to a series of drill rods and lowered to the bottom of the borehole. The top drill rod is fastened to a hammer which drives the sampler into the soil. Of the many types of hammers, the most common are variations on the drop hammer, which is manually operated, and the mechanical trip hammer. The driller lifts the drop hammer by pulling on a rope that is looped around a rotating drum, or cathead. By pulling the rope, the operator uses the friction between the rope and the cathead to pull the hammer up. The hammer is dropped by releasing the rope, thus reducing friction between the rope and the cathead. The trip hammer performs the same function, only mechanically. After the sampler is withdrawn from the borehole, the engineer disassembles the split spoon and inspects and classifies the material. The sample is then stored, such as in a sealed glass jar, and shipped to the lab for testing. If the split spoon contains 2 or more distinct soil types, each soil type should be stored separately, or they may get intermixed and subsequently misclassified in the lab. If there is any difficulty recovering a full sample, the split spoon may be fitted with a wire or plastic core catcher. In order to better preserve the samples, liners made of either brass, stainless steel, or plastic may be inserted into some split spoon samplers. A relatively simple and standardized method for estimating the compactness or stiffness of the soil in situ is the Standard Penetration Test, or SPT. This test consists of counting the number of blows of the hammer required to drive the split spoon sampler a specified distance into the ground. The essential features of the SPT test include a drop hammer weighing 140 pounds, falling through a height of 30 inches onto an anvil at the top of the drill rods, and a split spoon having an external diameter of 2 inches and an internal diameter of 1 3/8 inches, and a length between 18 and 30 inches. After the spoon is positioned on the bottom of the hole, the number of blows of the hammer required for 3 successive 6-inch penetrations are counted. The number of blows for the second and third 6-inch increments are added together to obtain the standard penetration resistance, or N value. The number of blows for the first 6 inches is not included in the N value since it may be affected by disturbed soil at the bottom of the hole. It is still recorded, however, as it provides a useful check on the variability of the deposit and the consistency of the overall results. There are numerous factors that can greatly influence the N value, and thus the field engineer must pay careful attention to the manner in which the SPT test is performed. Some of these factors will now be briefly discussed. Mud rotary drilling is preferred over hollow stem augering. If hollow stem augering is used, the hollow stem must be continually filled with water or drilling fluid to an elevation above the surrounding water table. Otherwise, inward seepage of water at the bottom of the hole could loosen the soil, thereby causing N values to be unrepresentatively low. This inward seepage could also erode soil into the auger stem, which, if mistaken for the bottom of the hole, could cause N values to be unrepresentatively high. It is recommended that the diameter of the borehole be 4 to 5 inches. As the diameter of a borehole is decreased, the penetration resistance is likely to increase. Side discharge bits should be used when rotary drilling because the jetting action of a face discharge bit disturbs the soil at the bottom of the borehole. Most drill bits can be modified to be side discharging by spot welding on baffles to deflect the drilling mud sideways. When sampling at depths less than 50 feet, A or AW drill rods with an outside diameter of 1 5/8 inches should be used. And for depths greater than 50 feet, N or NW drill rods with an outside diameter of 2 5/8 inches should be used. The heavier N or NW drill rods are recommended for the greater depths to maximize the transfer of energy from the hammer to the sampler. The split spoon sampler must have an outer diameter of 2 inches and a constant inside diameter of 1 3/8 inches. Liners may be used only in modified split spoons that maintain a constant 1 3/8 inch diameter inside the liners. If a modified split spoon with room for liners is used without them, the N values are generally 10 to 20% smaller. The amount of energy delivered to the sampler per hammer blow should be 2,520 inch-pounds, which is 60% of the theoretical maximum. The amount of energy delivered is dependent on many variables, including the type and weight of hammer, distance of free fall of the hammer, size and length of drill rods, tightness of connections, weather, and operator. If using a cat head and rope, the energy also depends on the condition and type of rope and the number of wraps around the cat head. If using a trip hammer, the energy also depends on its condition and type. The amount of energy delivered can range from 30% to 95% of the theoretical maximum. Since the N values are inversely proportional to the energy delivered, energy ratios of 30% to 95% can cause N values to vary by a factor of 3 or more. Mechanical trip hammers provide a more repeatable energy input, while the energy from drop hammers can vary as the driller becomes physically tired and slowly reduces the hammer drop height, number of blows per minute, and other variables. Thus, it is highly recommended that the energy delivered by a particular drill rig be calibrated on important projects. The blow count rate, or number of times the hammer is dropped per minute, can also affect the N value. During sampler penetration, negative or positive pore pressures may develop in the soil. A low rate of blows will permit more of the excess pore water pressure to dissipate between each blow than can occur with a faster blow rate. The result is different effective stresses and thus different N values. A rate of 30 to 40 blows per minute has been recommended. Even if these additional recommendations are incorporated in the already standardized standard penetration test, the results still only provide an indirect measure or indicator of the compactness or stiffness of the soil. Therefore, an engineer must be cautious in performing the test and analyzing the results. Thin-walled Shelby tubes are commonly used to obtain high-quality or relatively undisturbed samples. An undisturbed sample is one obtained with sampling techniques designed to preserve as closely as possible the natural structure of the material. These samples are suitable for shear, consolidation, and permeability tests, as well as for all tests performed on disturbed samples. However, a certain amount of sample disturbance is inevitable, regardless of the sampling method used, and thus the term undisturbed sample is only a relative term. Thin-walled Shelby tubes come in diameters from 2 inches to 3 inches, commonly have a length of 30 inches, and may be made of galvanized steel, stainless steel, or epoxy-coated steel. Tubes of much larger diameter can have difficulty retaining the sample. The lower driving end of a thin-walled tube is beveled to a cutting edge, creating a slight inside clearance. The upper end is attached to the drill rods using 4 hex screws and an adapter. To take a sample, a tube is attached to the bottom of the drill rods and lowered into the borehole. The sampler is then pushed downward from the bottom of the hole a distance about 5 inches less than the length of the tube. To minimize the sample disturbance, the sampler is pushed into the ground at a high constant speed. The sampler should not be driven by a hammer, as this increases sample disturbance. After the sampler has been pushed down, the drill rods are rotated to shear the end of the sample, and the sampler is removed. Excess soil at each end of the sample tube is carefully cleaned away, and metal discs are inserted to protect the faces of the soil sample. Microfine wax is then commonly poured against the metal discs to form a seal. Alternatively, special O-ring packers may be inserted against the soil inside the ends of the tubes, and then expanded to form a seal. Tubes are then stored vertically in a padded box for transport to the lab. Some disturbance to tube samples is caused by the in situ soil being distorted as it is squeezed into the sample tube. When the empty sampler begins its downward thrust, the adhesion and friction on the outside of the tube may cause the soil to rise into the tube faster than the tube is descending. On the other hand, after the tube is partly filled, the adhesion and friction between the tube and the sample oppose the rise of the sample. Under extreme conditions, the initial portion of the sample may act as a plug, capable of displacing soft clay seams or layers so that they do not enter the sampler at all. These conditions can be greatly improved by using a piston to close the lower end of the tube until the sampler has been firmly positioned against the undisturbed soils at the bottom of the borehole. The piston is then held at this elevation, in contact with the soil, while the tube is advanced around the piston and into the soil. Initially, the presence of the piston prevents soil from rising into the tube faster than the tube's penetration rate. Later on, downward movement of the soil sample is resisted by a vacuum that develops between the piston and the top of the sample. After the sampling tube has been advanced, the piston is fixed in its new position with respect to the tube. Both elements are rotated to separate the sample from the underlying soil, and the piston and tube are removed from the hole. Piston samplers with small area ratios are capable of furnishing excellent samples of cohesive soils, even if very soft and sensitive. The necessity for a separate piston rod rising through the drill rods to the ground surface can be eliminated by using a hydraulically operated mechanism such as the Osterberg piston sampler. Thin-walled tubes generally cannot be used in very stiff or compact soils without damaging the cutting edge or buckling the tube. Even if a tube could penetrate such soils, the resulting disturbance would be excessive. Under these circumstances, the pitcher sampler, in which rock coring techniques are adapted to tube sampling techniques, may provide better samples. While the pitcher sampler is being lowered into the hole, the thin-walled tube is suspended from the cutter barrel, and drilling fluid circulates downward through the tube and flushes the cuttings from the bottom of the hole. When the tube encounters the bottom of the hole, it is pushed upward into the cutter barrel, while the circulation is diverted outside the tube into the annular space between the tube and the rotating cutter barrel. If the soil is soft, the spring at the head of the tube keeps the cutting edge of the tube below the cutter barrel, and the tube is pushed into the soil just like ordinary tube sampling. If the soil is hard, the spring is compressed until the cutting edge of the tube is forced above the bottom of the cutter barrel. As the barrel rotates, it cuts an annular ring, leaving a cylinder of soil over which the sample tube slides. The tube thus protects the sample against erosion by the circulating fluid. In this manner, the pitcher sampler adapts itself to the stiffness of the soil. From the descriptions of these sampling methods, it is clear that all samples experience disturbance. This graph shows the results of 3 consolidation tests on the same heavily over-consolidated clay. 1 block sample, 1 borehole sample, and a remolded sample. Also shown on this figure is the ideal in situ curve, or zero disturbance curve, reconstructed using Schmertmann's procedure to correct for sample disturbance effects. As shown by this typical set of data, increasing levels of sample disturbance make it progressively more difficult to evaluate the in situ compressibility of clayey soils. This graph illustrates the stress-strain behavior of 2 samples of the same very stiff clay from Oakland, California. One obtained using a pitcher sampler, and the other obtained using a modified California split-spoon sampler. The severe disturbance caused by the split-spoon sampler is illustrated by the dramatically distorted and softened stress-strain behavior, as compared to the more reasonable behavior for the pitcher sample. More importantly, it must be realized that the pitcher sample is also disturbed, and its stiffness is also likely to be considerably less than the in situ stiffness. Disturbance to soil samples does not just occur during the sampling process. Additional disturbance occurs because of the unavoidable changes in soil confining stress. During transportation of the samples from the field to the lab, or during storage at the lab, especially if significant moisture content changes, temperature changes, or tube corrosion occurs. During extrusion of the samples from the tubes prior to testing, and during handling and mounting for testing. Generally, the better the quality of the sample, the more expensive and time-consuming its recovery is likely to be. For some purposes, such as designing the foundation of a light structure on stiff clay, the expense of obtaining high-quality samples may not be justified. On the other hand, when the compressibility or shearing strength of soft clay is needed to evaluate the settlement or stability of a critical embankment or structure, even the best samples may barely be adequate. Consequently, there is a need to establish a quantitative measure of the quality of samples, especially for soft clays and silts. This video has presented a basic introduction to some of the common drilling and sampling procedures used in geotechnical practice. There are many other methods that can be used for site characterization and soil sampling, including some that are considerably more advanced than the ones shown in this video. Regardless of the method, it is important that the geotechnical engineer be familiar with the tools and procedures that are being used in the field, understand how these tools and procedures can affect the results of lab and in situ tests, and appreciate the inherent uncertainties that are involved in characterizing subsurface conditions. Primary funding for this educational research project was provided by the National Science Foundation. Additional funding was provided by the Teaching Resources Center at the University of California, Davis. Tabor Consultants performed most of the drilling shown in this video. A special thanks is extended to Andy Tabor for their cooperation and support. CJ Supply graciously provided the drilling and sampling tools shown in this video. Special thanks to Bud and Alan Brodus for their cooperation and input. Valuable comments and suggestions were provided by Andy Tabor, Leslie Harder, and Michael Reamer. The assistance of Bill Sluice is also greatly appreciated. Narration by Christopher Peak and dialogue recording by Ned Jacobson.